Alright gang, here we go. So this is Chem 2 Unit 4. We're going to talk about redox reactions. Alright, so these are, redox stands for reduction oxidation reactions. Alright, so you hear redox, you know you're talking about something that's being reduced, something that's being oxidized. These are probably the most common type of reactions that exist. Alright, everything from, things, the way they're metabolized in your body, to rocket engines, to all sorts of things are really redox reactions. They're also my personal favorite. Anyway, so yeah, we're going to this particular section has a lot of new material. You know, acid bases you probably talked about in Chem 1, and so you've heard all that before. But redox reactions can be completely new, and there's a lot to them. All right, so buckle in there. Don't be afraid to pause and restart the video in certain sections as we go along. All right, so first off, we got to talk about some definitions. All right, so oxidation is defined as the loss of electrons. All right, oxidation is losing electrons, and reduction is defined as gaining electrons. All right, anytime something loses electrons, they have to be gained by something else. So they always come in pairs. All right, and so that's why they're called redox reactions, because if something's being oxidized, that means something else has to be being reduced. Okay, and so they always come in pairs. So here we've got calcium that's just sitting out here, and you've probably heard about the fact that like aluminum and calcium, they get oxidized if they sit out too long. And so essentially what happens is the oxygen in the air is going to steal these electrons from the calcium, and they kind of get implanted on the surface layer of your calcium, and you form calcium oxide. And so this transferring of these electrons is what drives a redox reaction. We'll talk a little bit more about why that occurs. Okay, so they always come in pairs. Now here's the kicker, all right? This is how you remember what it is. This stands for oil rig, right? It stands for oxidation is losing, and reduction is gaining, all right? So oil rig is the thing. All right. You might hear some heathens say Leo the lion says grr. If you hear that in another class, you have my permission to start throwing things at them. All right. Oil rig. Oil rig. Oxidation is losing. Reduction is gaining. All right. So how do we tell if something's losing or gaining electrons? Well, we use these things called oxidation numbers. All right. And so one thing to keep in mind about oxidation numbers, there's lots of rules that govern them, how we figure out how many oxidation numbers things have. But just remember that these are purely a bookkeeping method. Like, it doesn't mean that our atoms have the charges that we're talking about. All right, it's just our way of keeping track of how they're changing as they move across our chemical reaction. All right, so just remember that it does not imply that they have those charges. It's just kind of our way of keeping track of them. All right. So there's going to be a whole slew of rules, and just pause the video, jot them down, okay, and we'll do a bunch of practice problems to help you get used to them, all right? So anytime you have an atom in their elemental form, they have an oxidation number of 0, okay? So elemental form, so remember the diatom. So if it's diatomic, it's just chilling there in its elemental form, then it has an oxidation number of 0 automatically, all right? If you have a monatomic ion, okay, so this is like something that's just chilling out in space. So say you had Na+. Okay, so this would be a monatomic ion. The oxidation number on this ion is the same as its charge, and since it's 1 plus, then the oxidation number is +1. All right. One thing that I should point out is, remember how when we talked about charges, I made sure that you understood that we put the number and then the charge, positive or minus. So it would be 1 plus, 1 minus, 2 plus, 2 minus, etc. For the charges. Oxidation numbers are backwards. So you do the charge and then the number. And that's how we distinguish if we're talking about the oxidation number or if we're talking about the charge. All right. All right, so here's some more complicated rules. All right, nonmetals usually have negative oxidation numbers. Okay, but they can be positive depending on what they're paired up with. All right, so oxygen is almost always -2. Okay, unless it's in a peroxide. All right, so this would, like, classic example is hydrogen peroxide, which would be H2O2. Okay, and then it has a charge of -1. All right, so oxygen is usually -2 unless it's a peroxide where it's -1. Hydrogen is almost always +1 unless it's bonded to a metal. So if you had something like this, NaH is sodium hydride, and in that case the hydrogen has a charge of -1, or sorry, an oxidation number of -1. But almost always other time, like it's always going to be +1. All right, so that's one you can hang your hat on, is that hydrogen right there. Okay. Fluorine is always -1, always, 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 never anything other than that. And then any other halogens are almost always -1 unless they're with oxygen, and you form these oxyanions, and then they can actually be positive values. All right. One final rule is that if you take all the oxidation numbers for whatever molecule it is that you're talking about and add them up, the sum of all those oxidation numbers needs to equal the charge of the ion. Okay, so if it's a neutral compound, the sum of the oxidation number needs to equal 0. If it's a polyatomic ion or something else, then the charges of the oxidation numbers need to add up to be the ion. Okay, so make sure you count every atom, no matter how large the subscript is, when you're counting oxidation numbers. And this can get a little complicated. All right, so here we go. So this first question is pretty easy. It says, when is the oxidation state of oxygen -1 in all of these? Well, we already talked about one of our rules from before was oxygen is always -2 unless it's with a peroxide. And so this is the only one that's a peroxide there. All right, everywhere else your oxygen is going to have a -2 charge. All right, what is the oxygen state of the bold-faced elements in each of these? All right, so we have P2O5. All right, so P2O5. Now, the oxygen, remember oxygen, unless it's in a peroxide, is always going to be -2. So that means each of these oxygen is -2. So we're going to take, there's 5 of them, and it has a -2 charge. So that means overall, it's a -10. Okay, so this guy here, these oxygen, each of those is -2, and there's 5 of them, so it's -10. All right, now we have to ask ourselves, all right, what's the overall charge? Well, the overall charge of this guy is 0, so we need to figure out what the charge on this phosphorus needs to be, or what the oxidation number of this phosphorus. Now we know that the phosphorus has to equal +10, because if the oxygen is -10, that means the phosphorus needs to be +10. So therefore, each of these phosphoruses has to be +5. Right? Because there's 2 of them, and they need to add up to +5 or to -10. So therefore, the phosphorus has to equal +5. All right, so there's that guy. Sodium hydride, we already talked about this one earlier, but we can go ahead and do the work here. We know that each sodium is going to be +1. Okay, this guy's going to be, sorry, 1 plus. No, I was right, +1. Okay, and then, so therefore, a hydrogen has to be that hydride. And so it would be -1. So the hydrogen is -1. All right. Let's see. This is chromate. Okay. So we'll do the Cr2O7. Why don't you and it's got a charge of 2-. So why don't you pause the video, see if you can do it on your own. All right. So we know that each oxygen there's 7 oxygen, and each one has a charge of -2. So that means it's -14. However, the overall charge of it is -2, right? 2-. So that means we need each of our chromiums to equal a +16, all right? And there's 2 of them, so each chromium has to have an oxidation number of +8, all right? +8. All right, let's try tin bromide. So we've got SnBr4. All right, so we've got 4. Now, bromine is a halogen, and so it's -1. So therefore, we got -4 is what our tin needs to equal, or the positive value, +4. But there's only one tin, and it has a charge of 0, so that means that each tin has to equal +4. All right, so there's that guy. And let's do this last one, barium, BaO2. All right, so oxygen, there's 2 oxygens, 2 times -2, so this guy is -4, charge of 0, okay, so that means our barium, there's only 1 barium, so our barium has to be +4, all right, so there's how to do a bunch of oxidation number problems, okay. Now, why are these important? Well, lots of reasons, but, so we're going to talk about reacting in redox reactions, okay. So we have these things called displacement reactions, and these occur when you have an acid with a metal, okay? And we've seen this a dozen times between Chem 1 and Chem 2, that if you take a metal and you put acid in it, sometimes it'll make hydrogen gas, sometimes it won't. Okay, so here's an example. So we've done this one in class. We did magnesium, and we put hydrochloric acid in it, and it reacted to form bubbles, hydrogen gas, and then you also got magnesium chloride out. And so this is called a displacement reaction because you're starting with magnesium salt and it's getting displaced by the hydrogen, and the magnesium's getting dissolved, if you will, into the solution. All right, and we can tell which one's being oxidized and which one's being reduced by following the oxidation numbers. Okay, so magnesium's by itself and it's a metal, so it has an oxidation number of 0. Okay, and then we know the hydrogen and the chlorine would be +1 and -1 respectively. Now when they go across, okay, the chlorine is gonna, it's gonna go from being a -1 charge to being a -1 charge. So the chlorine doesn't change. So that means it did not get oxidized or reduced. Now the magnesium, though, went from 0 to +2. So if it went from 0 to +2, that means that it had to have lost electrons because electrons are negatively charged. So it lost electrons, so therefore that means the magnesium would have had to have been oxidized, right? Because oxidation is losing electrons. And then we find the hydrogen. The hydrogen went from +1 to 0. So that means it had to have gained electrons, right? Okay, so the hydrogen would have had to gain electrons because it went down in oxidation number. Okay, and so therefore magnesium, okay, lost electrons, is oxidized. Okay, and the hydrogen is reduced, right? Because it gained electrons. Remember, oil rig, oxidation is losing electrons. So it lost electrons, therefore magnesium is oxidized. All right, this is called the activity series, and this is kind of your go-to to figure out whether or not a reaction is going to occur. All right, so when we're talking about displacement reactions, okay, we're looking at hydrogen. Okay, so hydrogen's reactivity is right here. As you go up on this, the oxidation, your ease of oxidation increases. Okay, so anything that's above hydrogen on this list will be oxidized. Okay, whereas anything below the hydrogen will not be oxidized. So you could have hydrochloric acid in silver solution, and your silver won't ever get touched, won't ever get oxidized into one of these ions. All right, now, but like what we just saw with the magnesium, magnesium's up here, right? So magnesium, it started as a solid, got put in the acid, and then so it formed that magnesium 2+. Okay, and it got oxidized, and the hydrogen got reduced. All right. Now, so those are displacement reactions. So this is what happens. So that we can do the same sort of thing, but this is instead of using our acid and just producing hydrogen gas, we can actually use this to displace the metal that was there. Okay, so just hang on for a second. All right, so for example, they have copper. Okay, so this is just a copper coil, and they stick this in a solution of silver nitrate. All right, now because copper is higher up on the list than silver, copper is right here, okay, and silver is right here, copper will be oxidized by the silver. So therefore the copper is going to lose electrons and be oxidized by the silver and get replaced. So notice that your solution up here is, clear, and then it gets blue, and we know that copper solutions turn blue, so we really get copper nitrate here, and all the silver that was in there is getting plated onto your copper coil. So if you pull this copper coil out, you'll have a bunch of silver on the ends of it, or in the part that was in solution. So if you ever have this is like a really common thing called silver plating. Okay, so you can take your grandma's china and silverware and stuff like that, take it to a special place, and they'll do exactly this, and they'll use redox reactions and put silver back onto the silverware. So this is a great way to, restore old silverware, china, stuff like that. Well, not so much china, mostly silverware. And the old silver, plates and cups and stuff like that. All right, so anyway, so anything that's below the list won't get oxidized. So like silver, so if you try to use platinum, for whatever reason, I don't know why you would try to use platinum, or mercury or gold, and all those things are pretty expensive, but if you tried and you stuck a gold coil in there in your silver solution, it wouldn't plate. You wouldn't have that oxidation reaction occurring. Okay. All right, so we got to determine whether or not an oxidation reaction will occur. So which of these metals is easiest to oxidize? Well, gold is lowest on the list. So we can look at this guy right here. Gold is lowest on the list. Lithium is highest on the list. So therefore, lithium is going to be the easiest to oxidize. All right, and iron, sodium, and aluminum are all kind of in the middle of that. All right, which of the following metals will be oxidized by lead nitrate? All right, so this is what's in solution. Okay, and we want to see which of these three things, could be one, two, or all three of them, will be oxidized. So remember, so really essentially what we're doing is we're going to look at our activity series, and anything that's above the lead on the activity series will be oxidized. Okay, so lead, so we got the iron in there. Okay, there was copper in there, I'm pretty sure, and then what was the other one? Was it aluminum? Maybe I need to go look again. Nope. Zinc, copper, and iron. Okay, zinc is also above the lead. Okay, so zinc is up here. All right, so it looks like the iron and the zinc will be oxidized, but the copper will not. Okay. All right, so zinc and the iron, all right, will be oxidized by the lead. All right, writing equations for, we're going to skip practice exercise 1. All right, so we're going to write equations for a redox reaction. All right, so this is kind of where the rubber meets the road. Can you synthesize everything we've talked about so far? So we want to write the balanced molecular and net ionic equations for the reaction of magnesium and cobalt-2 sulfate. All right, so we got magnesium, okay, and so it's magnesium, so that means it's solid all by itself, and we're going to react it with cobalt-2 sulfate. So remember that 2 means it has a charge of 2 plus. Sulfate has a charge of 2 minus, so it'd just be COSO4, and this guy would be aqueous, all right, because it's an ionic compound. All right, and we could also double check our solubility rules just to see, but it is aqueous. All right, so this guy is going to react to form. Let's see, so we're going to get, so really we have to make sure that our reaction is going to take place. So we need to find magnesium and cobalt on our activity series. All right, so here we go. Magnesium is up here. Cobalt is down here. So that means cobalt will ionize or oxidize the magnesium. All right, so our reaction is good to go. All right, so our magnesium is going to be put into solution. So it'll be turned into magnesium sulfate. All right, aqueous, and remember magnesium has a charge of 2 plus because it's an alkaline earth metal. Sulfate is 2 minus, and then we're going to get cobalt solid out on the other side. So so that's that. So we can make sure, we want to make sure it's balanced. All right. Yeah, looks good. All right, so then we want to write the net ionic equation. So we could go ahead and write the complete ionic equation. The only thing that's going to change is this is going to be a CO2 plus and this is going to be SO42 minus. Okay, so your sulfates are going to cancel as you go across. All right, so that's going to make our life easier. So we're going to go, so our net ionic equation and turn into magnesium plus CO2 plus aqueous will go to magnesium 2 plus aqueous and cobalt solid. All right, so there's our cobalt solid. So now we need to decide, so that's our molecular and net ionic equations for that reaction. Now we need to decide which one's being oxidized and which one's being reduced. So in order to do that, we need to write out the oxidation numbers for these guys. All right, so let's see. So magnesium is a solid, or it's in its elemental form, so that means its oxidation number is 0. Cobalt, remember, if we have a monatomic ion, the oxidation number is equal to the charge, so that means its oxidation number is 2 plus. All right, same thing with magnesium here, it's 2 plus, and the cobalt is elemental, so that means it's 0. All right, so the magnesium goes from 0 to plus 2. That means it had to have lost electrons, right? Because it got more positive, so that means electrons went away. So that means your magnesium is oxidized. All right, magnesium is oxidized, and your cobalt went from plus 2 to 0, so that means it had to have gained electrons, right? Because its charge went down, electrons are negatively charged. So therefore, our cobalt would have had to have been reduced. Cool? Pretty sure that's it. Yeah, we'll talk about molarity and dilution and all that stuff in the next video. All right, so this is going to be all new materials, probably like close to the first time all year that you've had completely new stuff that we never talked about in Chem 1. So do make sure you do your practice problems, do lots of, rewatch the video if you need to, ask me questions. All right, and I'll see you on the flip side.